In this third part, we'll look at a few more examples of definite integration. Here we're integrating from 1 to 8, x minus 2 over the cube root of x dx. I'm going to divide each of these terms by cube root of x, and so I'll be integrating from 1 to 8, but what I'll have is x to the 2/3 minus 2x to the negative 1/3 dx. And when I integrate this, x to the 2/3 goes up to x to the 5/3, and that constant gets divided out, so there must have been a 3/5 here, minus x to the negative 1/3 goes to x to the 2/3, and it must have been minus 1/3 to begin with in order to get 2 initially. No, that doesn't make sense. In order to get 2, it must have been what? It must have been 3, because 2/3 times 3 is 2. And this will evaluate from 1 to 8, and it's nice that those are both perfect cubes. So when I substitute 8 in, let's see, I'll do this in two parts. The cube root of 8 is 2. 2 to the 5th is 32. And 32 times 3/5 is 96/5. Minus, still working with 8. The cube root of 8 is 2. 2 squared is 4. And 4 times negative 3 is negative 12. Minus, now I'm going to substitute in 1, starting with the first term. So that'll be 3/5 minus 3. And what's this going to be? First I'll deal with the fractions, so this will be 93/5 minus 9, and 93/5 minus 45/5, and so that'll be 48/5 for a final answer. Let's consider another problem. The integral of 2 plus sine x dx from 0 to pi. The integral of 2 is 2x, and the integral of sine x is negative cosine x. We'll be looking at this from 0 to pi. If I substitute in pi, this will be 2 pi minus the cosine of pi, and the cosine of pi is 0. No, pi would be, that's 0, that's 90. Pi is negative 1. And now if we look at 0, 2 times 0 is 0. And the cosine of 0 is 1, so this will be minus 1. And cleaning this up a bit, I'll have 2 pi, and then 1 minus negative 1, so 2 pi plus 2 is our answer. Let's consider another problem. So here we were integrating from 0 to pi fourths, 4x plus secant squared x dx. The integral of 4x is 2x squared. The integral of secant squared x is tangent x. And we'll be evaluating this from 0 to pi fourths. If I substitute in pi fourths squared is pi squared over 16 times 2 is pi squared over 8 plus the tangent of pi fourths is 1 minus, plugging in 0, I'll have 0 plus the tangent of 0 is 0. So our answer is just pi squared over 8 plus 1. Our final example happens to be an absolute value function. So it's the integral from 0 to 5 of the absolute value of 4 minus 2x dx. Now we're going to need to think about what the graph of 4 minus 2x looks like. or maybe that'll help us make sense of this. So let's graph that. So let's consider this graph of this absolute value function. Notice that it's really two linear functions. It's one linear function from 0 to 2, and a different linear function from 2 to 5. From 0 to 2, this is the line y equals 2x, negative 2x plus 4. And from 2 to 5, we have the function y equals negative 4 plus 2x. Right, another way to think about this is that with an absolute value function, 4 minus 2x, that could either be the function 4 minus 2x for some part, or it will be the opposite of 4 minus 2x from some part. And the opposite of 4 minus 2x is negative 4 plus 2x. But it's important that we tell which piece is where, because we're going to break this integral up then into two parts. The first part, going from 0 to 2, is the function 4 minus 2x dx. And we're going to add to that our second integral from 2 to 5, which was negative 4 plus 2x dx. And we'll integrate each of these respectively. So I'm going to kind of bring up my work down. The integral of 4 minus 2x is 4x minus x squared, and I'll be looking at that from 0 to 2, plus the integral of negative 4 plus 2x is negative 4x plus x squared, and that's going from 0 to 5. And I've always found it helpful to throw in a bracket there, just to help me keep organized. When I evaluate this first part, when I plug in 2, that's going to be 8 minus 4, which is 4, minus 0. So that's the first part, plus the second part. I'm going to change this. It's not 5 to 0, it's 5 to 2, 2 to 5. When I plug in 5, that'll be negative 20 plus 25, which is just 5. When I plug in, and that'll be minus, when I plug in 2, that'll be negative 8 plus 4, which is negative 4. So this will be 4 plus 9 for a grand total of 13. So we've got the algebra behind our definite integration of that absolute value function. Finally, we could have done any of these problems on our calculator, and you'll need to be able to do everything by hand and use your calculator when necessary. So let's do the last problem, but we'll do it on our calculator. So in order to perform a definite integral, the first thing we need to do is put our function in y1. So we said we're going to do the last problem, so the absolute value of 4 minus 2x. So to do that, to absolute value, I'll hit Math, slide over 1 to the right, num, and ABS stands for absolute value. I'll hit Enter, and I want to look at the absolute value of 4 minus 2x. And I'll graph that just so you can see it is what we thought it was. Good. And I'm going to quit out of this graph mode. We want to integrate this, so that's Math, option 9, for function integrate. And we want to integrate what we have in y1, so again I hit vars, 1 to the right is y vars, it's in function mode, and I want it y1. And my calculator needs to know with respect to what variable, so we're using x. And now I'll type in my limits of integration, the lower limit first. So in our case it was from 0 to 5. Close parentheses, and there's my notation. And I'll hit Enter. Calculator's doing a little work. And slowly but surely we get 12.999796, which is pretty close to what we got, which was 13. Notice that would round to 13. Now here's some issues. One, your calculator is basically doing a Riemann sum. The program is doing some type of a Riemann sum as part of a program, so it's going to be off just a little bit. But this is good enough, right? It's going to be off. It's going to be close enough to the exact to be good enough. Second, there is another way to integrate on your calculator, but for the AP purposes, you should only do definite integrals this way. The other way can be off by a degree of accuracy where you would get the answer wrong. So if you're going to do an integral on your calculator, you must do it this way for our purposes. And that covers the fundamental theorem of calculus.